Okay, this is better. All right. So firewalls lend themselves to amateur psychology, and last time I was at a firewall workshop, I talked about the 5 stages of grief. This time I'm going to talk about confronting our fears. And it's very important when you're really terrified by something. Do we have a stick, by the way, or some kind of pointer thing? It's very important to face your fears. In fact, I just looked it up this time. It's 6 steps. I'm not going to bother you with all 6 steps. It's very important to face them. You start writing them down. You start articulating them. What exactly are you afraid of? And so let's do that. Let's ask, why are firewalls bad? Okay. So no stick. Okay, no stick. Oh, it's coming. Great. So this is what I came up with. This is why I don't like firewalls. They seem to violate the equivalence principle in the sense that the equivalence principle tells us that the vacuum should look the same everywhere. Meanwhile, the Noether theorem, classical GR, tells us that a black hole horizon is vacuous, at least about a scrambling time after the last infall of matter. So if we insist on 2, then firewalls violate 1. Oh, thank you, Joe. All right. Then firewalls violate 1. And that's pretty bad. I care about the equivalence principle. I was brought up well. But the good news is that this is the only problem. It's a big problem, but it's the only problem as far as I can tell. And that has 2 implications that I think are worth stressing. At least this is my viewpoint, and the rest of my talk will be very much given with that viewpoint in mind. The first implication is nothing else matters. This is the only thing that's at stake. So I don't see any point in pursuing approaches that would reduce the drama at the horizon, less violence, but in which it still remains true that a local observer can detect horizon crossing. That's the only thing that's really bothersome about this. A horizon should not be something that you can locally detect when you cross it. Okay. Now, I will not talk very much about modifications of effective field theory. Steve and I have discussed this a lot, and I'm sure he doesn't agree with my viewpoint. But I think it provides an excellent example of this, where in the end, I believe in his model, a Rindler observer hovering near the horizon will find a different spectrum from a Rindler observer with the same frequency hovering anywhere else. And so you can locally detect the horizon. And I believe that this is a very general feature of effective field theories, non-local modification of effective field theory. Because the modes, and I'll discuss this in detail, the modes that you're fiddling with are centered very sharply on the horizon. And so your theory is going to go in there and say something special about these modes. It's very hard to make that not detectable. The other class of ideas that I will focus on today is identification of Hilbert spaces. And there it has been perhaps less obvious. People have focused on other types of criticisms. But I believe that here, too, it looks like it's going to be very hard to not make the horizon a special place, though in an ironic sort of way. The idea tends to fix the vacuum too well, so that you cannot have deviations from the vacuum when the equivalence principle demands that you have them. So this is what my talk will mainly be about. The second consequence of my viewpoint, I will come back to at the very end. And it's really the moral, I think, of this facing down your fears thing. You know, maybe things aren't so bad. The equivalence principle is only under threat if the horizon is actually vacuous. Now, it certainly seems very difficult to understand how it would not be vacuous. But I'm starting to believe that that may be the easier problem to solve. Okay. So I will start by discussing a point that I think is important. I've stressed this before, but so much of the attempts to fix firewalls, get rid of firewalls, have focused on the particularly sharp and beautiful argument that the AMPS paper gave, which zoomed in on highly entangled states of the near horizon zone with radiation that's already been emitted. That I think it's getting overlooked that the basic conflict is between 2 kinds of purity that are incompatible with each other. And it doesn't actually, in fact, it makes it worse if the near horizon zone is pure. So let me go through this. This can be stated at the level of quantum mechanics, so you don't have to think of X, Y, and Z as having anything to do with a black hole. This is strong subadditivity, and just make sure I understand the time. And these are three quantum systems. And let's suppose that the system XY is in a pure entangled state. That's captured by this statement here. And then strong subadditivity implies that there cannot exist a third system. So you can think of XY as the vacuum. There cannot exist a third system entirely distinct from X such that YZ is in a pure state. Okay. And otherwise, clearly, we'd have a violation. And you can think of YZ as basically the out state. It's modes that can be mined from the zone together with all the other Hawking radiation. And I'll try to be more precise about this. Nothing that I will say will be nearly as precise as what Don has said. So the people who thought that he was not sufficiently precise will be very disappointed with my talk. Okay, so equivalently, I'm just restating the same thing. Suppose the opposite, that the out state, what I'm calling here the out state, this thing YZ, is pure. And this is the key point. It doesn't matter if it's entangled or not. Y can be pure by itself, or it can be very entangled with Z. As long as YZ together is pure, then it's not possible that you can have some third system X such that Y together with X is pure if Y indeed has positive entropy, if Y by itself is not pure. Okay. And so far, I've really just stated secretly one aspect of unitarity, that the out state is pure. Of course, it has to be the right pure state, so this is not all we need for unitarity. And I have completely neglected to include any form of complementarity. Clearly, at some level, we're going to have to identify X with something on the outside, the inside of the black hole with the outside, otherwise we can't get the information out. But it's worth stating things at this level, going all the way back, to pretend we don't know about complementarity, because I believe that you'll see that this is not something this conflict's not something we can overcome with identifications of Hilbert spaces. There are other things we can certainly overcome with it, but not this. So now let me try to be a little bit more precise about what Y is and connect that to questions that probably not all of you have, because you've thought about this a lot, but maybe some of you haven't thought about it as much recently. Why is only the horizon affected by the firewall argument? Why not other places near the black hole or even far from the black hole? And this is where I think the role of mining is absolutely crucial. It's not so much whether you mine, but that you could mine, mineability. So let me discuss this. This conflict that I've just stated abstractly arises in the black hole geometry if we identify Y with any mineable mode, which is a mode that satisfies these two properties, that in the infalling vacuum, the entropy of this mode is large. It's order 1. But it is nearly purified. It doesn't have to be exactly purified, but it's nearly purified by some other mode with support inside the black hole, in the sense that together they have very small entropy. Okay? And then if this is closely related, but it's another important property, and it's not the same thing. If this mode were extracted from near the black hole and transported to infinity, this would decrease the area of the black hole. Okay? And because of this, and only because of this, the unitarity of the S matrix demands that whether or not I extract this mode, it has to be purified by the rest of the Hawking radiation. So F is supposed to label the final state, everything that gets out to infinity at the end of the day. And so what I called Z earlier on in the abstract discussion is basically everything that gets out to future infinity except for this one mode that we might want to mine. Yes?
Raphael, where in this argument do you use the fact that we're after the page time?
No, not at all. Thank you. Thank you. Not at all. Not at all. And this is really important. I will not use. Yeah. So I am not assuming that we're after the page time. And I I think that we focus too much on this issue. I think if there are firewalls, they will be there before the page time. I will, at the end of this talk, assume that we're after the page time, and I'll put a big red flag. I'm also not assuming that we're before the page time, by the way. It just doesn't come into the argument.
So you're not assuming any kind of scrambling, in order to get that there should be this entanglement extractable outside of the horizon.
That's correct. I have not assumed any particular entanglement or scrambling. Okay. That's right. I have not assumed any particular dynamics.
All right.
It's mostly because I will be answering mostly yes/no questions. Can you do something or not? Okay. So what are these mineable modes? Don characterized them pretty well, so I can go through this quickly. They live in the near horizon zone, so we have to have a picture of a black hole somewhere. So here's our black hole. Here is R equals 3/2 the Schwarzschild radius. And this is the zone. Okay, and this is where these modes live. And what you want to do is you want to pick up they basically are like Rindler modes if they're close to the horizon, and so they have a geometric progression of wavelengths, of proper wavelengths as you go out. Y. No. It's okay. I will not need more than this. You can.
We can't see it. We can't see it.
Oh, you can see it. Well, you know the panorama. Come on, Tom. Okay, I'm going to explain to Tom Banks.
It's behind your tower.
Here. You're going to get the. If I'm going to draw two pictures, I might as well put some variation in for your. Okay, good. So these modes, good. I'm going to go with this picture. These modes, they're you want them to be close to the horizon. They're localized really well over here, and they have to stay inside the angular momentum barrier over there. And you want to pick up a lot of these nodes, ideally. And right. And the other thing that's important is that they're only mineable modes if the black hole horizon, if the event horizon is a killing horizon at the time when I've drawn this picture. Okay, and I'll give you some examples. The number of independent modes like this is of order the area, in units of the cutoff, so maybe about the Planck cutoff. And so most of them come from very short wavelength stuff that's near the horizon. So no mining, no firewall. Okay, so here's example number one. Let's take an accelerated detector far from the black hole. Its acceleration is such that it has a Rindler horizon somewhere very far from the horizon, perhaps near the outside of the zone or very far from the black hole. And Bill Unruh taught us what happens, sees a thermal spectrum. From the inertial viewpoint, it's pair-creating particles. Okay? None of this has anything to do with the black hole. This could be happening very far. Of course, if one of these two particles, let's say the partner that didn't register in the detector, falls into the black hole, if it so happens, then the Hawking radiation is going to have to purify the remaining partner that stayed in the detector, just because the outside is supposed to be pure. But there's no problem, because when that partner went into the black hole mass got bigger. And so the radiation that is emitted by the black hole when it evaporates is more than it would have been if that thing had not landed in the black hole. And so it's consistent to declare that the modes were in the vacuum before I put the detector there and stirred up the vacuum. Okay. A second example, slightly more interesting, is, let's say, this black hole formed by the collapse of some shell, null shell, for those of you who can see it. Inside the null shell, it's just flat space, so there's a piece of event horizon inside the null shell that you can't causally detect that this is an event horizon, so there better not be a firewall there. And again, in that region, if you have an accelerated detector, it'll register particles, but the killing vector field that is relevant to an observer at infinity is not a killing vector field for which this part of the event horizon is a killing horizon. And so this type of particle detection does not decrease the mass of the black hole that forms. It will increase the mass of the black hole that forms compared to what it would have been otherwise. And so again, it's consistent to say that you had the vacuum there. Had you not disturbed the vacuum, it would have been the vacuum. And successful mining, all these conditions are satisfied. So you grab a wave packet that's well localized near the horizon, contains many Schwarzschild modes outside, and you drag it out in some way or another. And it doesn't have to be perfect. What happens is, if it's not perfect, is that you're going to create so here's right. The reason that you're extracting, I don't know what to do now, but so here's the killing vector field on the outside and on the inside of the horizon. I don't know if you guys can see this. And when you're detecting a mode here, the partner mode has negative killing energy because of the way the killing vector field is space-like inside the black hole. And that's what decreases the mass of the black hole. Now, if you don't do this very cleanly, then maybe part of the partner mode actually has support outside of the horizon, where it has positive energy, which can then fall into the black hole and make the black hole slightly larger. As long as that amount of energy that is added to the black hole is very small compared to the energy of the mode that you're extracting, this will not change the conclusion, because you're not giving the black hole enough extra Hawking radiation to emit so that you could fully ascribe the purification of the mode that you did extract to the extra radiation that was produced as a result of your unclean mining process. Okay. But of course, by unitarity, the Hawking radiation has to purify the guy you extracted anyway. And so in this case, it's clear that this mode could not have been purified by its would-be local partner in the vacuum, independently of whether or not I actually carry out this experiment. So this is the situation where the firewall argument hits. Okay. And for this reason, this is related to the discussion that Don gave, though not to ADS-CFT. I think the argument can be made more generally, perhaps not in quite such a rigorous context. We don't have to take these modes to go all the way up to the horizon, where they would have infinitely many nodes before you get to the horizon. You can put you can let their support start a little bit away from the stretched horizon, which is convenient because at the stretched horizon there may be new degrees of freedom that we like to fantasize about, like membrane degrees of freedom, and the modes may interact there in some way. So we can do this as long as the angular momentum barrier for this mode is far from the horizon in Planck units. Of course, for the modes that were already sort of Planck scale to start with, well, they were hopeless. Okay, so this is all I had to say about mining. Now I want to discuss old-fashioned complementarity, which I think works. Yes? Yeah.
Could we worry that, so, I mean, Adam had this recent paper, I don't know, a year ago, about various in-principle obstacles to mining.
Yes.
For example, it's hard to build a box that's really the right size. To really
thanks, Ben. That's good. It's a great question. There's actually two questions in there. One is, there's the question of how fast you can mine. How much can you speed up the evaporation process by helping the modes out, by dragging them over the angular momentum barrier? And there's some debate about that. I actually don't know if there's a debate, but anyway, Adam's paper disagreed, I think, with some earlier results by Unruh and Wald, and said it's actually slower than we thought, but you can still speed it up. That's completely irrelevant for the firewall argument, because we're just interested in whether, in principle, I can extract any mode that I set my eye on. I don't have to extract all of them at the same time. I don't have to extract them very fast. Doesn't matter. The other question is, are there obstructions to doing that in the first place? And my answer is maybe, but so far we haven't discovered any. And even if we did, we would still have a firewall problem for the S waves, which is unacceptable from the equivalence principle point of view, because you would only have power law suppression for very high energy modes near the horizon, and this would preferably happen right next to the horizon. This is not okay in the adiabatic vacuum. And so in the spirit of what I declared in the beginning, I'm just not interested. I don't think that looking for obstructions to mining is a productive way to solve this problem, because it's not going to solve it anyway. Also, we've had a year to try to find any, and so far, nothing. But, what's important is mineability. This is why I talked about mineability and not about mining. Because mineability defines which modes are affected by the argument.
No, that's right. But I mean, I think Adam said it's difficult to build certain kinds of boxes, which are basically the boxes you would need in order to. Oh, you can hang a string down there and have have some charge at the end and turn it on and off, and you don't have to use boxes. But let me not talk about it.
I think I said was relevant to what Raphael was saying, but also I don't understand why mining is relevant at all in what I've read. But you say the role of mineability, haven't just what you said, the role of mineability is irrelevant.
No. I have utterly failed to explain this point. I was trying to explain it by giving this contrast between mineable modes and non-mineable modes, and why there's a firewall argument for some and not for others. The non-mineable ones are, say, if I grab a mode that's in the part of the event horizon that's not a killing horizon inside the collapsing shell, that's a non-mineable mode. The reason that there's no firewall argument for it is that if I grab that with a detector, I actually increase the mass of the black hole that forms in this collapse. And so I can ascribe the purification of the mode that I did grab to the extra Hawking radiation that's emitted because I made a larger black hole. Similarly, if I have a Rindler observer very far from the black hole and the partner particle happens to fall into the black hole gets bigger. That makes up for, that purifies the mode I hold in my hand. So mineability is a situation where none of those objections apply. You grab the mode, the black hole gets smaller. Nevertheless, unitarity demands that it purifies the mode that you grabbed.
So, Raphael, just to mention, I think there are interactions which one can model, this will have to wait until my talk next week. Some people won't be here. Let me just mention that one can model that avoid these basic issues, and in particular, the mode is not really excited until you mine it and it escapes. So you don't have sort of a pre-existing excitation that is producing a firewall, say. So anyway, I can spell out more how that works, perhaps.
I look forward to that.
Yeah, I'm a little bit. I think you said that your mineable mode has a property that it's a mode outside the horizon, and you remove it, and the black hole immediately, the mass of the black hole goes down.
Yeah.
But my impression of semi-classical reasoning says that you have a black hole of a given mass, and you have radiation outside, and the total mass is sort of the sum, right? You have the mass of the black hole, and if there's radiation, if there's matter outside, it adds to the mass. So if you remove something from this zone, one might picture that what happens is that you then have more Hawking radiation, which then as a separate process occurs, maybe replacing the mode you removed and decreasing the mass of the black hole, and sort of restoring equilibrium or something. But it sounds like two processes, not actually.
It's a my help. They have some order 1 probability of getting reflected, order 1 to get out. Right? When one gets out, the black hole responds by getting smaller. Right? All that mining does is it helps the higher L modes out. I can also do it to an S wave and just make sure it really gets out, as opposed to just being confident. It's exactly this. There's some back reaction that makes a black hole smaller because you've got more energy far from the black hole. So because, as you say, energy has to be conserved.
Okay, but you're not distinguishing the mass of the black hole, quote, the mass inside a surface at the horizon, and the mass inside a surface at sort of twice the horizon radius or something like that. You're calling that the mass of the black hole.
There's two perspectives that you need to put together, I think, or at least I feel I have to put them together. One is that at infinity the mass is conserved, and the other is what's the difference between this situation and one where you just have unruh radiation? When you just have Unruh radiation, the detector has to pay the bill. The detector has to actually put in the energy for pair creating all these particles. And you'll find some back reaction on the detector. You'll have to put extra energy in to keep the acceleration going and so on. But hanging down a charge at fixed radius near a black hole by fixing it to some structure at infinity is free. So you have to understand how these two things go together. And the way that they go together is that in this case, the killing vector field, whose killing horizon this is also the killing vector field at infinity that defines the total energy. And in the Rindler case, it's not.
What? You had a question?
Okay, so let me talk a little about old-fashioned complementarity and why it cannot be extended to the vacuum. This is not really a dramatically new insight. In particular, I think it's something that Samir has been emphasizing for approximately 75 years. And where's Samir? I don't know. He's the chair. I want to publicly apologize to you, Samir. You were right. I was wrong. I gave you a hard time. You were right that there was something we don't understand about black holes. And if you hadn't kept talking about firewalls, I would have paid attention. About fuzzballs. But that just distracted me. And I should have paid attention. So can we? Here's the kind of complementarity we have to do anyway, right? There's matter falling into the horizon. We want the information to come back out. And so what can we do, right? We want a unitary S matrix. There has to be a unitary map from the matter that fell in to what comes out, if we want the S matrix to be unitary. In fact, we can construct it, right? If one gives you the unitary S matrix, well, all you need to do is take the matter that's inside the horizon, evolve it back out. Then he calls it the pull back, push forward procedure. You pull it back out, and then to past infinity, and then you push it forward with the S matrix that one gave us. And so now you've explicitly constructed a unitary map between the infalling matter inside the black hole and the out state. And in addition, it resolves the Xeroxing paradox. It's a wonderful thing. The question is, can we say that this map doesn't just hold for matter, but also for the infalling vacuum? Can we extend this map? So what I want to do is I want to identify any interior mode, let me just focus on one, with some scrambled, presumably, subspace of the out state, Hilbert space. Okay, so I'm just going to demand such an identification. This is going to be an argument that ignores many other problems, but that makes it very clean. And so let me proceed as follows. Yes.
Yeah, I didn't understand something in that equation. So is B an operator or a state?
It's a Hilbert space.
B is a Hilbert space.
Yeah, fat, whatever that's called, boldface letters are supposed to be Hilbert spaces.
It's a Hilbert space.
Yeah, so this would be the Hilbert space, let's say that's spanned by the occupation number eigenstates of the mode B tilde, and this would be the Hilbert space. So then this would be some scrambled subspace of the out state.
But only a finite number of occupation numbers? I mean, is that an infinite dimensional Hilbert space, a finite dimensional?
Yeah, okay. Let me go to the next slide. This is sloppy, you're right. I hope this will satisfy you better. So let me take the collection of mineable modes at all times and tensor them together in an indirect product. So of course, if I look at the mineable modes at one time and then shortly afterwards, I'll be talking about almost exactly the same degrees of freedom. But let me look at them at all times, take into account these overlaps, and define a Hilbert space that's spanned by all the states that those modes could have. So if I want a complementarity map, that better be finite, and it better be mappable into the out state, because the out state is spanned by, has dimension e to the a over 4. Okay. But of course, every mode that's at some point in the zone, in the mineable zone, by definition of mineable, because I could grab it and pull it out, has to be considered to be already in the out state. And every mode that arrives at infinity, whether or not I pull it out by hand, was at some point in the zone, and so the inclusion goes both ways. And so if I look at the collection of mineable modes at all times put together, it's the same thing as the out Hilbert space. Okay. Now it's actually not. My next step is going to demand the infalling vacuum, and you could object that, of course, when you form a black hole, you don't have the infalling vacuum. There's matter falling in. So let me, for the purposes of this talk, focus on a simple case where we make a black hole by the collapse of some star or a null shell or something once and for all. Nothing else ever falls in again. And let me just exclude the first scrambling time until the black hole settles down. At most, I'll be ignoring about log r quanta that will be emitted during that time, and which are certainly not sufficient to return information which could be of order a to the 3/4, at least for fast collapse. So let me focus on everything afterwards where I really need to have infalling vacuum at all times. So here's the infalling vacuum for some pair of modes, B and B tilde. Now, since the collection of all B modes already span F, and I'm mapping the B tildes, the partner modes, from inside the black hole also into that Hilbert space F, well, this, the state that's defined by all the B tilde pairs just specifies some state in F. There's no larger Hilbert space that I can talk about. And it completely specifies it. In some sense, it overdetermines it. But just naively looking at this, at the very least, it specifies a unique state in F. It's a pure state, but it would be unique, and that's a problem because it doesn't depend on the in state, and so information would be lost. So this is the reason why the attempts to apply complementarity to the firewall problem have focused on unconventional types of maps. A unitary map of the infalling vacuum to the out state overdetermines the out state and basically gives you a unique out state that would effectively lose information. But before I go to these unconventional maps, which for some bizarre reason have come to be called donkey maps, is Herman here? Yes. Before I just want to give one last praise to old-fashioned complementarity, because we're about to see how much more consistent it looks than what I'll describe next. Old-fashioned complementarity is doing just fine if we apply it to infalling matter only. It's causal in that we can allow the information to come out with a delay of one scrambling time after something falls in, and so you never have a problem that you can grab it and bring it back to the thing that fell in and see two copies of the information. It's linear. The map doesn't get confused if you take the superposition of two quantum states, and you always know what to do. And all of this is wonderfully consistent with the regime in which the pull-back, push-forward procedure is actually applicable, which is for one scrambling time after the most recent infall. After that, if you try to pull something back even further back, and this is something that Joe and collaborators pointed out, you're effectively using trans-Planckian modes in the procedure, so you don't really have control over it. So this suggests that indeed what happens is that a firewall forms after the scrambling time. If you throw something into the black hole further out after the new scrambling time, a new firewall forms, and so on. Okay, so now let's, before I get to donkey maps, let me talk about situations where no map can be defined at all. So I'll talk about two opposite limits in the next two sections, last two sections. One is the limit where I'm basically connecting to my first few remarks about double purity being the problem. If the zone by itself is pure, it's already clear that it cannot be part of the vacuum state. And there's no identification I can do between the interior and something far away that will change this fact. The question is whether we should care or not, and I'll try to argue that we should care about this. The second limit that we can study is where the zone is entangled in just the right way that by itself it looks it's in the same state whether you think of it as being part of the vacuum state, reduced to just the zone, or whether you think of it as being part of the out state, just reduced to the zone. So in that case, there's perhaps some hope for a map to operate. Okay, but let me start with a pure zone and try to convince you that this alone it gives you a conflict with the equivalence principle. So to make things as easy for me as possible, I'm going to worry about only one observer who plans to fall in at the time t and try to make things smooth for her. Okay. Now, the most general map that we can possibly consider is, in a sense, a many-to-one map where we take the out state, whatever it is, and map it to the inside and the outside of the horizon, the near horizon region and the interior, at the time t, in such a way that no matter what the out state is, we get the vacuum at the horizon. Okay. And the objection to this is quite trivial. The problem is that the out state and the near horizon region both contain the zone as a subsystem. And a general map, if I'm not careful, is going to assign two inconsistent states to the zone. In particular, if the out state is such that the reduced density matrix just for the zone at the time t is not thermal, not the one that I would have gotten by starting with a vacuum and tracing over the inside, then there is no identification that I can make of the interior with any other system that's going to change the fact that the exterior is already in the wrong state to be part of the vacuum. Okay. And actually, I'm talking about the pure zone, but that's just the most extreme example. As soon as the zone state is not the thermal state, I cannot do any identification that will turn it into part of the vacuum. So the following slides, I will try to argue for these 2 points. The first is that while you might say that these kinds of states are quite special and not generic in some sense, they're not that special in a different sense. They span the microcanonical ensemble of a black hole. And secondly, if we accept that, then I think we also have to accept that this alone is already a problem and a conflict with the equivalence principle, even if more generic states did not have firewalls. And I'll then come to these more generic states and deal with them separately. So here's my argument for why these states span the microcanonical ensemble. I hope this is not me. Okay, so let's consider a black hole in a box coupled to a heat bath. This is essentially the same thing, of course, as considering a large black hole in ADS, but I think there's no particular reason to restrict to that setting. We do have to put it in a box so that the ensemble is well defined. But of course, the states that I talk about, if they arise for a black hole in a box, I can always quickly remove the box and have somebody fall into the black hole. There are different time scales involved. So the question is, what kind of an object is the black hole? Is it like any other thermodynamic object or not? And I'm going to assume that it is. The black hole thermodynamics is valid and gives the correct entropy, and that it has a statistical interpretation. And that going over from the canonical to the microcanonical ensemble works in the same way as it always does. If that's not the case, this argument is useless. So what do we know about the black hole? Well, we know for sure that the black hole consists of the zone in the sense that, well, these are degrees of freedom that I can extract from the black hole so that they're degrees of freedom that can be exchanged with the heat bath. Okay. Now, a lot of the arguments that try to develop maps to get rid of firewalls also appeal to additional degrees of freedom, perhaps horizon or membrane degrees of freedom. So in order to include this, we should include this in order for these arguments to be covered by what I'm going to discuss. So there's some extra degrees of freedom H, which by definition are not semi-classically accessible. Okay. In particular, H, the information in H has to come out somehow. And if H is not semi-classically accessible directly, then the only way it can happen is that by coupling to the zone modes, as they get redshifted, as they move away from the horizon, at some point they they come under the cutoff, they're part of the semi-classical regime, or similarly, when they fall back in, they go over the cutoff, and that's the place where we can allow them to interact with H. But not somewhere else, otherwise I could just access H directly. And so H does not couple directly to the heat path, but through the zone B. It's the picture that at least I have in mind is you have a cavity, a black body cavity. The outside walls are coupled to heat bath. There's black body radiation, and then in the interior hovers a ball that interacts very locally near the surface of the ball with this radiation. So it's indirectly coupled to the heat path as well. Okay, so now I would argue that as for any large subsystem of a thermodynamic system in the canonical ensemble, the entropy is additive. What do we know about the entropy? Backup thermodynamics fixes the total entropy to be A over 4. It doesn't actually matter in this argument that it's A over 4, but just that it's fixed. SBH, the two systems together, have some entropy. Subadditivity implies that the separate entropies of these two systems have to be at least that. If they're greater than A over 4, then there is some mutual information between the two systems. But I would argue that we've defined B to be degrees of freedom that can be exchanged with a heat bath, the mineable degrees of freedom. Therefore, in this particular case, we know that SB plus SH must be equal to the black hole entropy, because otherwise mutual information would build up between the heat bath and the black hole, and the entropy in equilibrium would not be constant. So as a result of the canonical entropy being additive, this basically means that I can treat B and H as separate systems, each controlled by the temperature of the heat bath, and go over to the microcanonical ensemble separately for each of them. Okay. Now, maybe I have to exclude some very small layer. This would also be true for the ball hovering inside the black body cavity, where there's an interaction region or they have complete control. But this will affect only a small subset of degrees of freedom. So maybe I will not get exactly a pure state for B. I will get something that has that's mixed, but it will still not be the correct thermal state. So first, let's go over to the microcanonical ensemble for B alone. Okay, so we know the size of this ensemble. It's now a finite dimensional Hilbert space because it's the microcanonical ensemble. Of course, we're doing the usual thing. So usually you have a canonical ensemble. You go over to the microcanonical ensemble by looking at the expectation value of the energy, fixing that to be the energy of the microcanonical ensemble, and then in the thermodynamic limit, you're guaranteed that the number of states of that energy is e to the entropy of the canonical ensemble. That's all I'm using here. Okay. Now, if that sorry.
So can you just walk me through this for Minkowski space? So let's take Minkowski space and split it into the left part and the right part. Now, would you say that the microcanonical ensemble with respect to the Minkowski Hamiltonian factorizes into?
I have no idea how to even discuss this. I mean, the setting is completely different, right? I cannot put Minkowski space. I cannot couple it to a heat bath. I cannot extract modes and get energy at infinity. I don't see the connection at all. No. If you try to couple Minkowski space to a heat bath, it's unstable. So it's not a well-defined setup at all. We can try to make it well-defined, but maybe we should do that after my talk. Yeah. No. The zones, it's a thing. It's like the radiation in that cavity. It's a thing. You can grab it.
Your argument that when you're in equilibrium at something like the Hawking temperature, the number of modes in the zone or the number of degrees of freedom is comparable to the Bekenstein-Hawking entropy? Or what if it's much, much less, for example?
Well, it has a scale like the area, and the question is what the cutoff is. So you could make the cutoff such that it's a lot less. That doesn't affect this argument.
Okay, so in particular, the cutoff could
But
be
whatever you make the cutoff, that's going to also affect how bad the firewall is. If you make the cutoff at lower energies, then the firewall you can be sure about is less horrible than if you make it at higher energies, but it's still a firewall. So it's like the CC problem again. It doesn't really help to move the cutoff around. Okay, so in this case, the microcanonical ensemble factorizes because we can go over separately for each Hilbert space for B and for H. Let me call these microcanonical Hilbert spaces that are finite, B bar and H bar. Like any outer product of Hilbert spaces, it'll be spanned by a product state basis. And now B by itself in every basis element is pure. The zone is pure, so it can't possibly be part of a vacuum state no matter what identifications you make. Okay, so there's a firewall in every basis state in a complete basis for the black hole. That's my claim. Now we have to discuss whether anybody cares. Okay, so let's take a step back for a minute and let me argue what are acceptable deviations from the vacuum. The adiabatic vacuum, you've got a detector floating around. What is the chance that this detector is going to see a particle whose energy is much greater than the inverse curvature scale? Well, the chance of that is e to the minus the curvature radius divided by the wavelength of the particle you want to see. It's exponentially suppressed. And this is beautifully confirmed by black hole thermodynamics in the sense that in the zone of a black hole away from the horizon, this is exactly the chance that you're going to get hit by an unusually hard Hawking quantum. Right? That's Boltzmann suppressed. E to the minus the energy of that Hawking quantum divided by the Hawking temperature. Moreover, such unusually hard quanta constitute a Hilbert space. In other words, if I have two of them, I can take two such states. I can take a linear superposition. It will also be such a state with such an energy, equally suppressed. It's in the same class. Okay. So they constitute a Hilbert space. It's not like they only form a basis, but if you take superpositions, it's a different kind of state. What they don't do is they don't span the full Hilbert space of the black hole because they're Boltzmann suppressed. They span a very tiny subspace. Okay. And finally, I think this is quite important as well. In free fall, if you're falling through the zone, there's nothing special about the horizon as far as your chance of detecting such particles goes. You might hit one of these, equally unlikely, but you might hit one anywhere in the zone, or even far from the black hole. I mean, if the black hole emits a rock, it can hit you very far from the black hole. The horizon is not very special from the viewpoint of this phenomenon. The complete firewall basis that I've identified is very different. These states are rare, but in a completely different sense. They're not Boltzmann suppressed. They're rare in the sense of the Haar measure. If you have a large system, you divide it into two systems. You take a random pure state, Haar random pure state for the whole system. It's very unlikely that it's going to be a product state. So yes, they're very, very rare, but they're rare in the wrong way. They don't constitute a Hilbert space, since if you take the sum of two product space, it's not a product states. It's not a product state. But they do span the full Hilbert space. It's just that they don't constitute it. So it's all wrong. Most importantly, I think, the associated hard quanta are sharply localized to the horizon. You're not able to encounter them absolutely anywhere else. At least nobody's exhibited any other class of states that would have the same property anywhere far away from the horizon. That would be naturally part of the black hole Hilbert space.
So Haar
Yeah.
rare and Boltzmann, they're both exponentially suppressed in the dimension.
Oh, in some ways, Haar rare is much
I'm
worse.
asking about Haar rare versus
Yeah.
Boltzmann rare. They're both exponentially suppressed. Is it one's e to the minus the entropy?
No.
This is a submanifold of zero
Yeah, Haar rare is you take a Hilbert space and you identify certain states which are very atypical in that Hilbert space, but they don't form a subspace. So they're very rare in that sense. They're rare at the e to the minus entropy level. Sorry, e to the minus number of states level. Yeah, e to the number of states level. Yeah. the temperature, energy doesn't come into it. It's not a Boltzmann suppression. So it's a very different kind of suppression. It's that kind of rarity that's the answer to the question, what's the chance that my randomly picked state is a product state? Yeah.
So this is a really naive point. This may be, okay. But if in every product state you had even just an exponentially small probability of not experiencing a firewall, then that would be perfectly consistent with a linear combination of those product states having definitely no firewall, right? So.
Yeah. So maybe there's some way around. So, I mean, I would think that you can have very good product states. But in any case, if you, I think it's not even necessary that you have this admixture. Because, firewallness might be measured by some non-positive operator, or you might have some nonlinear reconstruction map for the interior that allows effectively for the same kind of cancellation. So let me come to that situation next. Yeah.
Yeah, and maybe this is going to become relevant later, and I should have asked it earlier. Earlier you had the B and the H system.
Yeah.
And then you had an equation saying that SB plus SH was SBH.
Yeah.
Meaning that there's no mutual information between the two.
Right.
And I thought these systems were interacting. These are macroscopic systems that are interacting.
They're
with
interacting.
each other.
But
So
the point is that they're no longer interacting by the time that B can exchange energy with the heat bath. And this would also be a problem, again, for the system with the ball and the black body radiation. Otherwise, mutual information would build up between the system and the
mutual information always builds up.
And the heat bath.
Any systems that interact build up mutual information. That's a very common.
It has to. My point is just that in the thermal equilibrium, the entropy, the canonical entropy, cannot change.
Okay.
Otherwise, of course, if we're not yet in the equilibrium, this is absolutely right. Now, I probably have to be careful that I don't run out of time. This is what Samir is telling me.
5 minutes. If you want to stop for general questions at some point, you can just.
Yeah. Now, I do need to get to the donkey maps. So, life after page. This is the first time in the talk that I'm specifically referring to the page time, so that I can engage with ideas that invoke nonlinear maps or non-unitary maps to reconstruct the vacuum. And a particularly famous one is ER equals EPR. So I will assume now that the black hole has less entropy than the radiation has, that it's already emitted, and that it's in a typical state, in which case the mode B can be approximately purified by a highly non-unique scrambled subsystem. Let's call it E sub B, respecting AMSs, of the early Hawking radiation. Let me defer all further questions to the end, because otherwise there's just no, sorry. So this B has high entropy, but it can be very nearly purified. Of course, there's also an exact purification if I have access to the entire out state, but right now I'm just interested in a purification to extremely good approximation, and this just happens to be true. Learned this from Freskel and Hayden. Now we want to avoid this entanglement conflict with the vacuum being a pure state. So let's identify B with E sub B. B tilde, thank you. The interior with the purification of B in the Hawking radiation under some state-dependent map. And let me first show that the donkey map must self-correct for interactions. Okay, and I'm going to begin, and please hold off on the protests. I'm going to begin by treating this purification of the zone mode, E sub B, as unique, which it isn't. And I'm also not going to worry about the beautiful considerations that Daniel Harlow and Hayden added to this, which is that it might be very, very hard to actually extract EB from the radiation that's already been emitted. It might take very long. There are arguments about this that have been given, and I have nothing to add to that. For now, I'm going to ignore and pretend that you can just couple to EB. So let me write down the state. I have some pointer that hasn't interacted with anything yet. And then this is just the BEB state, which I've already labeled the states of EB in such a way that conveniently the donkey map looks trivial. It's just going to map 0 to 0, 1 to 1, and that's going to construct the vacuum. Okay. And now let's suppose that the pointer measures this purification in this basis. Okay, and then we have this state. Okay, this is just some unitary evolution that leads to the state, sometimes called a pre-measurement. And then tracing over the pointer, or having the pointer coupled to other stuff that we can then trace over, but we might as well just trace over the pointer, it's simpler, gives us decoherence. It gives us a mixed state, which the coherence is lost. And this is a mixed state, so there is no map that I can possibly write down that's going to map this to a pure state. No map from EB to B tilde that's going to map this into a pure state. And that is not okay, because what I've just described is generic, modulo the things I haven't dealt with. Hawking radiation in real life is going to interact with huge environments. It's going to get measured by other stuff. It's going to run into the CMB. It's going to run into galactic dust. Okay. So if there are firewalls, as soon as the Hawking radiation runs into an environment, that's just as bad as if there are firewalls if it doesn't. We shouldn't. That's not acceptable if we don't like firewalls. Okay. So the map has to adjust. It has to ignore the fact that it has to not ignore the pointer. Okay. It has to consider the entire system, which is still in a pure state, and we have to define a new donkey map, which looks like this. Okay. And now this state under this map, as you can easily see, becomes the infalling vacuum. Okay. But this is important. What's particularly funny about this is that this has to happen if we don't want firewalls for the infalling observer, no matter whether the infalling observer has any idea what the black hole interacted with, whether it interacted with anything, I mean the radiation. Okay. Okay, so let's say we have to do this. Fine. The problem is we can also use the pointer to measure a mode near the horizon, B. The thing that EB was the purification of. Let's just measure B directly. Okay. This results in exactly the same state that I just wrote down. Well, because I've suppressed positional information, but it looks the same. And we could have more pointers. Again, we could have classical records. Bob knows that the outcome was 4, let's say, for this reason. Okay. So Bob and the pointers stay outside the black hole. They don't fall in, but they move out of the way. And many, many years later, while this mode is still in the zone because it's a very big black hole, Alice falls in. She has no idea what's going on. She encounters B. And her theory, as we've just discussed, says that black holes that B tilde, the interior, must be identified with whatever purifies B, which in this case involves the measurement apparatus. Yeah, it's going to take 2, I hope. Yeah, sorry. 2. So the donkey map is going to adjust again. Okay. We're going to identify B tilde with whatever purifies B. And the result is the infalling vacuum. And that's a problem because, of course, it didn't have to be Bob who did this experiment. It could have been Alice herself. She could have ordered the experiment. She could be seeing the pointers if they didn't disperse. Alice is unable to find anything but the vacuum, even in cases where she should have been able to excite the vacuum. And that violates the equivalence principle just as bad. The vacuum is not behaving the same way everywhere. Okay. You can detect the location of the horizon. Now, this sounds pretty crazy, but it's just a logical conclusion from what I said before. You might ask, what is the description of this in Alice's point of view? And I'm not sure. It's not my job to give a consistent description of this, because I don't think it is consistent. But it reminds me of final state quantum mechanics. There's a final state being imposed on the horizon, which makes the horizon special. Now, we could have more complicated rules. But we can't base the rule on the state because it's the same state in both cases. We'd have to base the rule on where the interaction took place. Was it in the zone or in the radiation? Hard to make this sharp because we can interpolate between the two limits. Take EB to the zone and the pointer, arrange a 3-way interaction, dial the strength of the pairwise interactions any way you want. Limitations from computation or from back reaction, well, we can consider larger systems. Let me truncate to 0, 1 occupation numbers. If E is now just a computational qubit, a simple Hawking quantum, I can measure that. F is the rest of the Hawking radiation. B is again a pointer. Initially, the state is something messier looking, where this simple Hawking quantum is mixed together with other stuff in the Hawking radiation. Again, I can measure either B. In this case, the vacuum had better be destroyed by the measurement, so I must trace over the pointer. Or I can measure the simple Hawking quantum, in which case we don't want the vacuum to be destroyed, and so we must retain the pointer. Okay. It's very hard to write down a general rule that will distinguish between these two types of measurements. And neither back reaction nor hard computation prevents a simple Hawking quantum from being transported to the zone. Okay. People talk about quantum error correction. I have difficulties with this analogy, but I think it cannot help in any case because the error can be arbitrarily large. It can affect all the quanta. There's no reason why not all of the Hawking radiation should interact, which destroys all purifications. Even though there's some redundancy, you can destroy all purifications of B. And so the challenge for these kinds of approaches would be to nevertheless come up with some rule that discriminates between these different cases. So let me close with this. If we can find, I think it might be easier to find a rule for why the adiabatic vacuum breaks down after scrambling time. You have to be careful that you don't conflict with causality, Lorentz invariance, and with the fact that we don't produce particles in cosmology all the time. But if we can do this, then firewalls aren't really anything to worry about. Thank you.